A few months ago, my aunt emailed members of my family saying that she found an old cassette tape of my grandmother describing a children's game to her when she was little. And unfortunately, the recording has a lot of noise.
Everybody has to catch hold of the other person's thumb and stack them up, and be sure the one that's on the bottom knows all the rigmarole, so they're the ones that have to tell the story at the last.
It's almost impossible to hear anybody speaking through all of the noise in the video, but I thought I could use what I've learned studying optimization to fix this problem and remove the noise. The first step in any applied math problem is to build a model. We're going to try to transform this problem into the problem of minimizing f over some constraint set C. Some common constraint sets include the set of vectors with non-negative elements, or vectors that satisfy a certain set of linear equations. In order to guarantee global convergence of our algorithms, we often require f and c to be convex. To find an appropriate f and c, we need to take a closer look at our signal. This spectrogram of the audio clip shows how much of each frequency is represented in the signal. We see most of the structure lies in frequencies near zero, and all of the higher frequency information is scattered noise. This suggests that to find a denoised version of our audio, we want to find a signal that's close to our noisy signal, but also has minimal high frequency information. To do this, we minimize the sum of two components, one measuring the distance to our noisy signal, and the other component measuring the amount of high-frequency information in the signal. If we minimize both simultaneously, we'll find a denoised version of our audio clip. We choose D to be the discrete cosine transform, and the parameter lambda controls the effect of each term on our eventual solution. Now, the way we've set the problem up here doesn't exactly regularize for low-frequency sounds, but the effect is about the same, and we'll describe it this way for simplicity. Okay, all that remains is to fit our model, which we do by solving the optimization problem that we derived. And I will do this in MATLAB. So this MATLAB script sets up our problem. I'm only going to load 20 seconds of audio for now, so it's a small data set and it should run faster. For now, I'll set lambda equal to 1 over 10, and we can change this value if we don't like our solution. And I'll run the code for 3,000 iterations. So I'll be solving the optimization problem using proximal gradient descent, which is a standard method to solve these types of problems. Let's run the code and see how we like the solution. Okay, we see proximal gradient descent is pretty slow, even with a small amount of data. So let's go do something else while this code runs. MATLAB is finished running. Let's go take a look at the solution. So the first thing I want to see in this solution is the spectrogram like we looked at before. So things look nice. All of the high frequencies have very little energy, which is a good sign. But as I'm looking at it, I see there might actually be too much regularization going on. We usually don't want all of the components set equal to 0 at high frequencies. So let's see what this sounds like. It seems we've set too many of the frequencies equal to 0, and we've moved too far away from our original signal. This implies that our choice for lambda is too large. So let's try this again with a smaller value of lambda and see if we get a better solution. This is the spectrogram of our solution with lambda equal to 1 over 1000. We see that while most of the signal is contained in the low frequencies, we still have a lot of information in the high frequencies to make the signal more complete. Let's see if this gives us a better sounding result.
Everybody has to catch hold of the other person's thumb and stack them up, and be sure the one that's on the bottom knows all the rigmarole, because they're the ones that have to tell the story at the last.
This recording has much better quality. We can hear my great-grandmother describing a game called Fist Stalk, which is a children's game that was played in the American Midwest around the early 20th century. Besides being a cool family heirloom, this example introduces several areas of research in modern optimization. An active area of research is understanding how to transform real-world problems into optimization problems. A great example comes from control theory. Consider an inverted pendulum with an actuator applying torque on the first link. The goal is to find a controller for the pendulum by maximizing its region of stability. Most solvers formulate this problem so that stability is only guaranteed for the maximizing controller. In the AnySauce toolbox, we formulate this problem differently so that we can quickly find controllers that are guaranteed to be stable. The following example shows the inverted pendulum swinging up and then balancing using a controller found with the AnySauce toolbox. Our model is useful because it allows us to find controllers quickly. Solving optimization problems quickly is a field of research on its own. When fitting a model, researchers are constantly looking for faster algorithms. Again, we hope to prove that these algorithms are faster, not just observe it in practice. An example from my research is the algorithm Stochastic Average Recursive Gradient, or SARG. SARG replaces the gradient with a random approximation of the gradient that is easy to compute. SARG also can incorporate momentum to minimize the objective faster. Applying SARG to the minimization problem in this video shows that stochastic gradient methods are often faster than full gradient methods like proximal gradient descent, and sometimes much faster. Thank you for listening, and I hope I've represented well the many applications of optimization.